welcome to my channel. In this video, I'm going to discuss how to write the laboratory manual for doing the electrical circuits laboratory experiment, that is experiment for series and parallel resonance. So first of all, if any student is watching this video, so if they want to note down this manual in their laboratory observation, then they have to follow some rules. That rules that I will discuss, and later I will proceed to discuss about this series and parallel resonance manual. So first of all, what students should do is, in their observation notes, on the right side page, they must write the title, they must write the date, experiment number, they must write aim, apparatus required, theory, procedure, formulae, calculation, theoretical proof, practical proof, precautions, and results. Okay, so all these must be written only on the right side pages. Even if left side pages are empty, don't worry about them. Just you must write all this content only on the right side pages. Okay, on the left side pages in your notes or observation, what you have to do is you must draw the circuit diagrams, observation tables, and model graphs. Okay, so on the left side pages in your observation or notes, you must draw the circuit diagrams, observation tables, and model graphs, whereas on the right side pages, you must write the aim, apparatus required, theory, procedure, formulae, calculation, theoretical proof, practical proof, precautions, and results. Okay, so all these must be written only on the right side pages. Now let us see the title of the laboratory manual experiment, which I am going to discuss now, that is series and parallel resonance. Title is series and parallel resonance. So write down the title. Now aim of this experiment. Here we are going to do the experiment to determine the quality factor and bandwidth for both series RLC circuit as well as for parallel RLC tank circuit. So here I have written two parts for this aim. One is for series RLC circuit, another is for parallel RLC tank circuit. So my first aim is to find the quality factor and bandwidth of a given series RLC circuit using hardware as well as MATLAB software. So if you people in your laboratory are doing the experiment only for hardware, you no need to write and MATLAB software. If you are going to do the experiment for both hardware and MATLAB using both software and hardware, so whichever software that you are going to use, you can write it down instead of MATLAB software. Here I am going to use only MATLAB software. That's why I have written MATLAB software. So another aim is to find the quality factor and bandwidth of a given parallel RLC circuit, RLC tank circuit, using hardware and MATLAB software. So if you are copying it down in your notes or observation, you people can pause this video and write down the aim in your notes and follow the rules which I have discussed at the beginning of this session or at the beginning of this video, mentioning that what are all the terms that are to be written on the right side and what you have to write on the or the draw on the left side. So aim should be written on the right side. Next, apparatus required to do this experiment. So here we are going to do both hardware experiment as well as software, MATLAB software experiment. So apparatus required for hardware experiment, both for series and parallel resonance circuits. The apparatus required table is same. So here the equipments required are signal generator. You can even call it as a function generator. Its range is from 0.1 Hz to 10 megahertz, and we need one signal generator, and we need a CRO. Okay, so that CRO whose range is 20 megahertz dual channel CRO we need one, quantity 1. We need a circuit board, quantity 1. We need a decade resistance box 1. We need decade inductance box 1. We need decade capacitance box 1. We need an ammeter whose range is 0 to 25 milliamperes, which is rectifier type, and we need one ammeter, so I have mentioned one. We need an voltmeter of 0 to 10 volts. Type is rectifier type, and the quantity required is only one voltmeter is required. And we need some connecting wires, or we can even use patch cords or connecting wires, whichever are available in our laboratory. We need a bunch of connecting wires or patch cords. So the quantity required I have written here as required number, as per your requirement. Okay. Required number means as per your requirement. As many as you require, you can use them. So just copy it down in your notes or observation. Pause the video while copying down this tabular column in your notes. So these are the apparatus for hardware experiment. So for software experiment, we need only MATLAB software. Therefore, I have drawn here only one row with 2 columns. Software required is what? MATLAB. That's it. So let us see the circuit diagrams for series resonance RLC as well as parallel resonance. So first of all, I have here, you can see series resonance RLC circuit. So you can see RLC connected in series to an AC voltage source. Okay, this is it. So our source voltage is Vs, and since all the elements are connected in series, all these RLC are connected in series, same current I will flow through all these elements. Okay, this is our source voltage. You can draw the circuit. Pause the video and draw the circuit. Next, parallel RLC tank circuit. So here, so this is our RL connected in series, and across RL capacitor is connected, okay, in parallel to this RL. So this R, you can call it as the inductive reactance. Okay, so this is our AC voltage source Vs. So the source current is Is. The current is coming out of the source, and so the current is coming out of the source Is, and at this junction this Is current will divide into IRL and ISC. I'm sorry, IRL and IC. So the IC current will flow in this branch, IRL current will flow through R and L, and here once again IRL and IC will add up, and IS current will once again return back to this source. So this is an RLC parallel resonance tank circuit. You can pause the video and copy it down if you are if you want to note it down in your notes. Now let us see the practical circuits. Those were theoretical circuits. Now let us see the practical circuit for doing the hardware experiment. Series RLC resonant circuit. This is our series RLC resonant circuit. I have not written RLC. It's okay. So I might have written RLC. It might have been more better if I write RLC. So this is our series RLC resonant circuit. So here you can see R of 100 ohms, L of 0.05 Henry, and C of 0.1 microfarad. So resistance value is 100 ohms, inductance value is 0.05 Henry, and capacitance value is 0.1 microfarad. Micro means 10 to the power of minus 6. This is the symbol of micro. This is the symbol of micro. Micro means 10 to the power of minus 6. Okay, 0.1 into 10 power minus 6 farads. Okay, so 0.1 microfarad. So this is 0.05 Henry. So if you want, depending on which type of decay detector box you are using, if 0.05 Henry is not available and if millihenry is available in your inductance box, so you can convert this Henry into millihenry. So 0.05 Henry is equal to 50 millihenry. 50 millihenry. Milli means 10 power minus 3. Okay, so this is our signal generator or function generator. Okay, this is our source here. So across the signal generator we have to connect a rectifier type voltmeter of 0 to 10 volts, and in series to all these elements an ammeter must be connected, which is also rectifier type of 0 to 25 milliampere range. Okay, so we need a rectifier type voltmeter of 0 to 10 volts range. We need a rectifier type ammeter of 0 to 25 milliamperes range. Okay, so this is the practical circuit. So we have to do the experiment using this circuit. You can pause the video and later you can draw the circuit in your notes. Now let us see parallel. So this is a parallel RLC resonant tank circuit. So here R and L are connected in series. R value is, resistance value is 100 ohms, L value, inductance value is 0.05 Henry. You can, if required, you can convert that 0.05 Henry into millihenry. So 0.05 Henry is equal to 50 means 50 millihenry, 50 millihenry, and our capacitance value is 0.1 microfarad. Micro means 10 power minus 6, 0.1 into 10 power minus 6 farad. Okay, so this is our signal generator, this is our source. So across the signal generator connect an rectifier type voltmeter whose range is 0 to 10 volts, and in series to this tank circuit. Okay, this is our tank circuit. This is our tank circuit. In series to this tank circuit, connect an ammeter, which is also a rectifier type, whose range is around 0 to 25 milliamperes. So the apparatus required here are same for both series and parallel. We are going to take the same apparatus to do the experiment, resonance experiment for both series and parallel circuits. So this is our circuit. So you can pause the video and copy down the circuit diagram in your notes. Now for doing the software experiment, so I have written a program for series resonance. So you have to type this program in MATLAB. So first of all, you have to type CLC. CLC means clean screen. So first of all, you have to clean the screen. So before, as soon as you start to write the program, so in order to clean the screen, CLC, you have to type CLC semicolon, CLC semicolon, CLC semicolon to clean. It means the clean screen. Next, you have to type clear all semicolon. Clear all means to clear all variables from the current workspace. Okay. So in order to clear all the variables from the current workspace, you have to type clear all. Next, you have to type close all. Close all means you have to close all currently open figures. Okay, whichever scripts or figures that are open, so those must be closed. Okay, because you are about to write a new program in the MATLAB, so you have to close all. So don't forget to mention these semicolons. Now type small r is equal to input within brackets, enter the resistance value, okay, and semicolon. Next, capital L equal to input, enter the inductance value, semicolon. Next, C equal to input, enter the capacitance value, semicolon. Next, V is equal to input, enter the input voltage value, and semicolon. So here within these brackets, your wish, you can write anything. Okay, so here I have written enter the input voltage, but I spoke enter the input voltage value. You can write your voltage value, or simply you can write enter the input voltage. It doesn't matter. Okay, it will take as it is whatever it is written here. Okay, next, F. F means frequency. So frequency, we are going to vary the frequency here. So we will start with 100. Initial value of frequency is 100, and the final value of frequency we are considering it as 5000, and we want to vary from 100 to 5000 in tens. Okay, we want to vary the frequency from 100 to 5000 in tens. Means first reading is 100, second reading is 110. I'm sorry, not reading. First frequency is 100, second frequency 110, third frequency 120, fourth frequency 130, and so on up to 5000. Okay, so in divisions of 10, the frequencies will vary from 100 to 5000. So F equal to 100 colon 10 colon 5000 semicolon. So you can pause the video and you can write down this program. The program further continues in the next slide. Okay, next, XL equal to 2 into 5 into F into L. So inductive reactance. XL means inductive reactance. 2 pi FL. Formula is 2 pi FL. So you can't write 2 pi FL in MATLAB. You have to type XL equal to 2 into pi into F into L semicolon. Next, capacitive reactance XC. XC is equal to 1 by 2 pi FC. So what I have done here is XC is equal to, I have started with a bracket 1 dot divided by within again bracket start 2 into pi into F into C, double time. Since there are two starting brackets here, I have closed both the brackets. I have put dot here. The reason behind that is our frequency is varying, F is varying, isn't it? So for all frequencies, XC has to be calculated. Capacitive reactance has to be calculated. That's why you have mentioned, you have to put this dot here and semicolon. Next, x is equal to xl minus xc. xc we have calculated, so x equal to xl minus xc semicolon. Next, impedance. Z is impedance is equal to square root sqr3 bracket start, again bracket start r square, this is r square, r to the power of 2, this is r to the power of 2 bracket close plus, again start the bracket, x dot to the power of 2 close the bracket. So the dot, if dot is there, that means that for different frequencies this x value has to be calculated again and again. So you will get many impedance values for different frequencies. For each frequency you will get one impedance. Okay, so close this bracket, semicolon. Next, current in the given circuit. Current is equal to I equal to V dot by Z semicolon. So dot means, so there are different impedance values for each frequency. So for each impedance value we have to calculate the current. So you will get different currents. So that's why I equal to V dot by Z semicolon. Next, plot F comma I. So we have to plot frequency with respect to current. If we want grid, you can type the grid 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 semicolon. Okay, so this is optional, grid is optional. So if you want, you will get, if you type grid here you will get the grid, otherwise it's not compulsory to type this grid semicolon. Okay, but you can type this grid dot grid semicolon. Next, x label. Okay, on x-axis x label, you want frequency to be written on the x label, so you write x label within brackets frequency semicolon, y label within brackets current semicolon. Okay, so you will get the x label as frequency in the plot and y label as current for this plot. So you can pause the video and copy down this program. Next, program for parallel resonance. Again CLC. As I have already mentioned, CLC means clean screen. So CLC semicolon. Next, clear all. Clear all means all the variables from the current workspace, they all have to be cleared. So clear all. Okay. Next, close all. So whichever page is open, all other pages which are open, all those pages or scripts must be closed. Okay. Next, type R equal to input, within brackets enter the resistance value semicolon. R means resistance, L inductance, L equal to input, enter the inductance value semicolon within brackets. So C equal to input, within brackets enter the capacitance value semicolon. Voltage V, input voltage, V equal to input, enter the input voltage semicolon. Next, frequency. So F equal to frequency, F is nothing but frequency, F equal to 100 colon 10 colon 10,000. So here my initial value of frequency is 100, my final value is 10,000. So I want each the frequency to be the multiples of 10. So 10 10 with the difference of 10 10, the frequency will vary from 100 to 10,000. So first frequency is 100, second is 110, third one is 120, and so on up to 10,000. It will vary. Now XL, that is inductive reactance, is equal to 2 pi 2 into pi into F into L semicolon. And impedance, I am going to calculate here impedance of R and L. Okay, R is what? This is my R, and we know impedance units is ohms and L unit is not ohms, so we have to consider inductive reactance XL value. So ZRL equal to square root of start the brackets, two brackets, and r to the power of 2 r square. Okay, close the bracket plus again start the bracket xl dot to the power of 2 xl dot. Why we have put the dot? Why? Because for different frequencies impedance has to be calculated. So close the brackets and semicolon. Pause the video and copy down the program. So program continues. So admittance YRL, we have determined the impedance. Now we will determine the admittance. We know admittance is reciprocal to impedance. YRL is equal to 1 dot by ZRL. So why we have put dot here? Why? Because there are different values of impedances. So you will get different values of admittances. Now XC, capacitive reactance, is equal to, start the bracket, 1 dots by divided by, again start the bracket, 2 into pi into F into C, brackets close, semicolon. So next, capacitive impedance. Capacitive impedance is nothing but capacitive reactance. So I have simply written ZC is equal to XC. Okay, so why? Because we know if I want admittance is reciprocal of impedance. So that's why capacitive here, if only capacitor is there, its impedance will be equal to the capacitive reactance. Okay, if only capacitor is there, that's why I have written ZC is equal to XC semicolon. Next, I want to determine the admittance of the admittance across the capacitor. So YC is equal to 1 dot by ZC. So capacitive admittance I have got. I already have admittance of RL element. So what is the total admittance? Both elements are connected in parallel. So total admittance is Y. So Y is equal to YRL plus YC. That is the total admittance. Now what is the current in the given circuit? I is equal to V dot into Y. Okay. So voltage, V is the input voltage into the admittance Y. So I is equal to V dot into Y. So plot F comma I semicolon. So the plot is for frequency versus current, and grid semicolon, X label frequency, Y label current. So you can pause the video. You can pause this video and write down this program. Now observation table. So for hardware experiment, okay. So for hardware experiments, for series resonance, write down serial number, oscillatory voltage, that is input voltage V, frequency and current. Okay, frequency in hertz, current in milliamperes. So voltage is maintained constant throughout the experiment, at least around 5 volts. So voltage will not vary, it will remain same. For different frequencies, note down the current. For series resonance, so same thing you have to do for parallel resonance also, same table. So you can pause the video and note down this table. Next, for parallel resonance, same serial number, oscillatory voltage, frequency and current in milliamperes. So you can pause the video and you can note down the table of column in your notes. Okay. So So once you have done that, you can plot the graph between frequency and current for both parallel resonance as well as for series resonance. So after plotting the graph, so actually for software experiment, there is no need to you will not have any values. Why? Because directly you are typing plot in the program itself, you will get the plot. So there is no observation table for software experiment. Observation table is there only for hardware experiment. So if we are able to plot the graph for hardware experiment, and if you get the plot for software experiment, later what you can do is you can determine bandwidth, resonant frequency, and quality factor parameter values. So for that I have drawn one more table. So parameters that I want to note down in this table are resonant frequency, bandwidth, and quality factor. For series resonant and parallel resonance, theoretical values, practical values, theoretical values, and practical values. So theoretical formulas, using theoretical formulas for the given circuits, you can determine the resonant frequency theoretically, bandwidth theoretically, and quality factor theoretically for series circuit. And for parallel resonance circuit, tank circuit also, you can write down the theoretical values. After doing the experiment, you can note down the practical values for resonant bandwidth and resonant frequency, bandwidth, and quality factor. Resonant frequency, bandwidth, and quality factor. Okay, you can write it down this. You can note down the values in this tabular columns. So these values are only for hardware experiment. For software experiments, since it is the same circuit, no need to determine the same parameters again and again. Same plot you will get for software also. For hardware graph that you are going to do on the simulograph sheet. Okay, so for the hardware experiment, you are going to use a simulograph sheet to plot the resonant plot. Okay. So frequency versus current plot for both series and parallel. So for hardware experiment values, you are going to write it down, theoretical and practical values. For software, no need to write it down. Why? Because you are directly getting the plot. Okay, so unnecessarily it's wastage of time. For the same circuit, no need to determine values again and again. If you want, you can do that from the plot that you get. You can add one more column here. So practical values for hardware and practical value for software, practical value for hardware and practical value for software. You can add one more column. I have not added here. So if you want, you can do that. Okay. You can do it. So you can add one more column here. Any, I want to insert column here. It's not showing any insert option. So if you want, you can add one more column here for hardware and software, not to distinguish between hardware and software, practical values. Here once again you can do that. Okay. Next, you can pause the video, you can copy down this table. Next, theory. Theory should be written on the right side. For writing the theory, you can leave at least one or half page. You refer to the textbook. Okay, you just refer to the textbook and write the theory in your observation or notes. So you can leave one or 1.5 page in your observation to write the theory. Next, procedure. So for doing hardware experiment. So connect the circuit as per the circuit diagram. for series RLC and for parallel RLC tank circuit. Set the voltage of signal generator to 5 volts. Vary the frequency of the signal generator over a wide range in steps and note down the corresponding ammeter readings. Draw the graph between frequency and current. You can pause the video and you can note down the procedure. Few more steps are there, that is those steps are in the next slide. So you have to plot the graph. You have to plot the graph for both for frequency versus current, frequency on the x-axis and current on the y-axis on a semi-log graph sheet for both series RLC circuit and for parallel RLC tank circuit. You can pause the video and note down the procedure in your notes. Next, what you can observe here while after doing the experiment is that in case of series RLC circuit, current first increases, then decreases, and the value of frequency corresponding to the maximum current is nothing but our resonant frequency, that is F0. In case of parallel RLC tank circuit, we can observe that the current first decreases, then increases, and the value of frequency corresponding to the minimum current is our resonant frequency. So from both series and parallel circuit graphs, we can calculate the bandwidth and quality factor, and we can tabulate it. So you just pause the video. Okay, just pause the video and note down, write down this content in your notes. Next, formulas that are required for theoretical calculations. So formulas for parallel resonance. So resonant frequency F0. F0 is the resonant frequency. F0 equal to 1 by 2 pi root 1 by LC minus R square by L square. Next, quality factor Q0 is equal to 2 pi F0 L by R, and bandwidth BW is equal to F0 by Q0. So these are all the formulas for parallel resonance. So theoretically, you know the circuit, you know RLC values from the circuit diagram. You can calculate these parameters theoretically, and you can tabulate it in the tabular column. If you are noting it down in your notes or observation, you can pause the video and note it down in your observation. Next, formula for series resonance. For series resonance circuit, resonant frequency F0 equal to 1 by 2 pi root LC. Quality factor Q0 equal to 1 by R root L by C. Bandwidth is equal to F0 by Q0. You can pause the video and note down the formulas in your notes. If you want to note it down in your notes, you can pause it and note. So these are the formulae for both series and parallel resonance to determine the F0, Q0 and bandwidth theoretically. So let us see the formula for practical calculations. Okay. So formula for series resonance after doing the experiment. So from the graph of series resonance circuit. So whatever graph that you get, as I've already told you, as frequency varies for series resonance circuit, as frequency varies, I will take pen. For series resonance circuit, as frequency varies, this is current. This is, my cursor won't listen to me. Current will increase and decrease. Okay, current will increase and decrease. Okay, so this is the point when current is maximum. So the frequency at which current is maximum is known as F0, that is resonant frequencies. I'm just erasing all. Okay, so current will increase and decrease as frequency varies. So from the graph you have to determine the bandwidth F2 minus F1 and quality factor Q0 equal to F0 by bandwidth. From the graph of series resonance, bandwidth and quality factor F0 directly will get it from the graph. Similarly, formula for formula for parallel resonance, I have written here series resonance. Similarly, formula for parallel resonance from the graph of parallel resonance circuit. Bandwidth, same formula, F2 minus F1. Quality factors are same, F0 by BW. Okay, resonant frequency by bandwidth. So just note it down. So these are the formulas. So these calculations, they can be performed after drawing the graph for both series resonance and for parallel resonance circuits. So I will show you the model graphs in the further slides. So you can pause the video and note down these formulas in your notes if you are not copying down the manual in your notes. Okay. So now, using the above theoretical formulas and practical formulas, you can perform the calculations. Leave at least 2 pages in your notes or observation. At least 2 pages to do the calculations later. So if you are copying it down in your observation, leave at least 2 pages and you can proceed further. Okay, so let us see the model graph. For series resonance, this is our graph. X-axis frequency, Y-axis current. Okay, X-axis is frequency, Y-axis is current. So as frequency varies, current will increase, will reach to a maximum value. Later, current will decrease as frequency is further increased. So the current at certain frequency, current is maximum. That frequency is known as F0, that is resonant frequency. Okay, so at maximum current, resonant frequency is obtained for series resonance circuit. And if you take the if you take this maximum current and divide it by √2, okay, you'll get some value. Okay, so for that value, you just locate that value of current on this y-axis, and from that point, wherever it is located on the y-axis, if you draw a dotted line, horizontal line intersecting this current versus frequency graph. Wherever it intersects, it will intersect at 2 points on this plot. So the first point wherever it intersects, from that point draw a vertical line towards x-axis. Another point wherever it intersects, draw a vertical line towards x-axis. So this frequency at which this intersection takes place, that is known as lower cutoff frequency. The frequency at which this intersection takes place is known as upper cutoff frequency. So this is denoted by F1, this is denoted by F2. So F1 is lower cutoff frequency, F2 is upper cutoff frequency, F0 is resonant frequency. So what happens for series RLC circuit? As frequency varies, current will gradually increase, it will reach a maximum value and later it will decrease. So you can note it down in your notes or observation on the left side page in your observation. Okay, so this is the graph that you will get for series resonance. Let us see the graph for parallel resonance. You can pause the video if you want to draw this in your observation. Just pause it and draw it in your observation later. Let us see for parallel resonance. So you can see as frequency varies, current is also varying, but what is happening to current? Current gradually decreases. Okay, as frequency increases, current gradually decreases. After reaching the minimum value of current, current further increases. Okay, current further increases. So at certain frequency, current is minimum. This is minimum current. So that frequency is known as resonant frequency for parallel RLC circuit. So for parallel RLC resonant circuit, at minimum current, resonant frequency is obtained. That you must remember. Okay, and now multiply this minimum current with √2. You will get some value of current. Locate that current on the y-axis. Okay, wherever, so let us assume this is the location. From there, draw a horizontal line which will intersect this plot at 2 points. Okay, here it is intersecting as well as here it is intersecting. Wherever it has intersected this plot, from there draw a vertical line towards x-axis. Again, from this intersection, draw a vertical line towards x-axis. So wherever it intersects the x-axis, consider it as F1. Wherever it intersects on this x-axis, consider it as F2. F1 is known as lower cutoff frequency, F2 is known as upper cutoff frequency, and the resonant frequency is F0. So this is the plot that you will get. You have to draw this after doing the experiment. You have to draw this graph on the semi-log graph sheet. You can pause the video and you can draw this graph in your observation or notes. Now, let us see the precautions that are to be followed while doing the experiment. So, keep input voltage constant while taking the readings. Avoid loose connections. Avoid parallax error while taking readings. So, these are the precautions that are to be followed while doing this experiment. So, you can copy it down as it is in your notes on the right side page in your notes. Last result. So since after doing the experiment, you must write down in the result that I have determined the quality factor and bandwidth for the given series RLC circuit as well as for parallel RLC tank circuit using both hardware and MATLAB software. That's it. That is the result. After doing the experiment, you can write it down. So I hope you have understood how to write the manual. And if you have any queries, any doubts, or any suggestions if you want to give, you can mention it in the comment section. Okay, if you like this video, just click on the like button so that this video can reach many people who want this manual. And if you have not yet subscribed this channel, you can subscribe my channel. So if you want me to make video on any other concept, you can mention in the comment section. Thank you for watching this video.